All right, happy Monday. So let's get started. I hope everything looks okay with the setup. As you can tell, they upgraded the podiums, but I wasn't quite ready for the upgrade. But I think I got everything sorted, but I might be a little slightly discombobulated. All right, well, let's start our midterm. Well, a couple of announcements, I guess, before we begin. So for the in-person lab folks, right, we will have our regular lab on Wednesday. So we'll do lab 5. And then if you're online, you do have the extra lab practicum. So that's the online test. So if you're in-person lab, right, don't worry about this. Again, just kind of working on that throughout the week. And then of course we'll have our midterm in person on Wednesday. Otherwise, it's open up online. And again, for equal purposes, if you guys in person want to take it online, that's also fine. And do keep in mind, it is all open note. So hopefully, right, not worry about cheating. And then obviously, like, don't use AI or Google. And so just be honest with that. So, and AI isn't always correct, but you only cheat yourself ultimately. All right, any questions before we get started? Oh yeah, and we won't have a quiz for. I just realized that, right? So I didn't build one on the My Open Math. I may like still kind of build one later, but it'll be like not for a grade. Yeah. Yeah. I forget what it is online, and then in person it's like 2 hours, so it's probably like about the same. And, again, if people have time accommodations, that should be taken care of in Blackboard, but maybe like double check with me. And same thing in person, but yeah. Not necessarily. Yeah, you could just do it at home. So that's the option as well. Is like if you want to do it at home, but I mean some people test better like in person on paper, like it's totally up to you. Uh I mean maybe let me know just so if like half the class doesn't show up in person, I at least know you're taking it online. But yeah, I'm like I said, I'm okay. I'd be also curious if anybody in person wants to take it both times and see if there's a large discrepancy because that's what I've been trying to field out as well. But yeah, like I said, just trying to make the course more equitable for the online and in-person folks. So everybody's getting the same treatment and the style of learning they want and just kind of consistency across. But like I said, I tend to curve the grades anyways. So like even if the tests are maybe lower in person, I try to curve appropriately. So like I said, most people get like an A or B in this class. It's a 100 level course, right? We're not here to like bust GPAs or anything. Here to learn. So all right, so let's get started on the review. And if there are questions, right, I'm happy to take questions. I haven't received any emails about questions, but I'm happy. Like I said, that's a great way to communicate. Send me a picture. Hey, I'm looking at this. This is my work. I don't quite get it. But I haven't received too many questions. But all right, so let's kind of go through. I'll go through kind of the style of questions that will be asked. So we'll do the classify the following. So we have diamond, methane, cheese, but let's do like cheddar. Well, let's do two types of cheese. So do cheddar and then versus what about like a jalapeno? Oops, I can't spell. Jalapeno cheese. Lots of stuff in it. Yeah. Yes, I think I need to, yeah, I need to share it, but I'll post the link. But I think there should be some other like midterm, what's it called, resources as well on there. But yeah, I'll post this. So jalapeno cheese, so lots of stuff, right? Like we'll put green peppers or jalapenos and red whatever, pimentos, whatever they put in cheese, etc. And then C21 H30O2. So try those. Yeah, because we're doing midterm review today, so we're not starting chapter 5 till next week. All right, let's see what we got. What is a diamond? Oh, and I should have specified classify the following as element, sorry, compound or homogeneous or heterogeneous mixture. So I don't know if we need another minute after that. So what's a diamond? Excellent. So element, remember it's one, it's all carbon. Methane, good. So one of those small molecules you should know. What about this first cheese? So I was trying to go for, right, like a just a block of cheddar. Homogeneous. Yeah, and you can just yell it out. Oops, if I could spell. And then what about jalapeno cheese? And I was trying to be pretty obvious with it, right? That it's speckled with a bunch of Excellent. So heterogeneous. And then this last one, so C21. You guys are fast on the gun here. So compound. Any questions about that one? Or any of these other ones that have maybe come up in the homework? All right, let's see what else is kind of on your exam. So then there will be some questions with conversions. So let's practice some of those. So let me pull up a few. And so you could have some with like made up units. So we'll try this one. So convert 467,000 kilogoops to floof if there are 19.5 goops in a floof. So try that one for a few minutes. Give people like another minute or so, and then we can yell out or go over it too. So what do we get for our answer? I'm still kind of sketching it out. What's the, you said, so, do you have that in like scientific notation? That's more in the range I was looking of. So I was sketching it out, right? You have to go, it's all just unit conversion. And so I kind of try to throw you guys off with this kilogoop, right? So that's 1 times 10 to the third here, or 1,000 goops in 1 kilogoop with your units canceling. And then from there, we just have to go from goops to floof, right? Because we want floof at the end. So I'll put floof on top. And there are 19.5 goops. So goops cancel. And so that's what I got. I can punch that in. So yeah, I don't know if you wanted to say your number again, if that's what you got. I'm better with scientific notation. So we can punch that in if people need that punch. So times 1,000 and divide it by 19.5. And then 1, 2, 3, 4, 5, 6, 7. So did we all get that? Any questions on that? So I see some yeses. All right. So let's try another one. So we'll use our metric units this time. And right, again, open note, so use your handout for your conversion factors, for your metric conversion factors. So let's try convert 7.76 times 10 to the negative 11 megameters to picometers. So again, we'll give people time to kind of work that out before we sound off answers. So do we have answers yet for this one? 7.76 times 10 to the 7. That's what I get. Is that what other people got? So remember, there's two different ways to convert this one. So we could have either gotten the direct conversion factor. So what are megameters? So 10 to the 6, and then what was pico? So 10 to the negative 12. And so then some people might see this, or again, we could divide it out if it's not obvious, right? So 1 times 10 to the 6 divided by 1 times 10 to the negative 12. So then that gives us our factor of 10 to the 18 difference here. And so some people, and if you want it to really be fast and do some mental math, right, you just, well, now we have this factor of 10 to the 18 plus our negative 11, and so that does give you the answer of 7.76 times 10 to the 7 picometers. So I could write that out, right? So if that made sense to people. The other thing we could do, so let me write this, kind of our one-step conversion out instead of just doing it super shorthand, but trying to give you guys like math tricks too, right? So you can get faster. All right, so we're trying to go to picometers, so then small units in the big units, so that means we have 1 times 10 to the 18 picometers in 1 megameter. So again, that gives us that answer. Or did anybody do kind of the two-step conversion? So going from, right, our megameters. So I would go from megameters to meters to picometers is the other way to do it, right? So that you're always comparing to a base unit. So did anybody try it that way? Yes, no, yes. Remember, now's your time to ask questions. I'm sure you guys all have like the same questions or similar. So let's sketch this out, right, what we started with. And then let's go to our base unit. So again, mega, we said 10 to the 6. So 1 megameter, 1 times 10 to the 6 meters. And now we need to go from meters to picometers, so put meters on bottom to cancel out again, right? And then 1 times 10 to the 12 picometers on top. Again, more tiny units in the big one. So does that look good for this setup? And then again, you can start adding your exponents. So negative 11, right, plus 6 plus 12. So that gives us our 18 factor again. Or we can punch it into the calculator. So now I'll just punch it in again just for clarity's sake. And then count it out. 1, 2, 3, 4, 5, 6, 7. So same answer either way. All right. Kind of make me nervous on the conversions. Let's try periodic trends for a second. And we can always go back to topics, but again, ask questions, it's your time. So now let's do, so which has the largest radius? So which has the highest ionization energy as well? So we'll think about those two things for a minute or so. So let's start with the largest radius. So which one has the largest radius? So phosphorus, so I like that. And do we have a Y? So yeah, basically our effective nuclear charge. And so we can just say, right, we're adding more electrons in same shell, aka same radius or distance away. So again, what he was saying, right, the distance between our nucleus and then our electron cloud. And so again, we're putting more in that same radius. And so that leads to greater effective charge. So more pull effectively, again, right, pulling it closer. Good. Excellent explanation. All right, so then what do you think for the highest ionization energy? What do we remember? So chlorine, and right, kind of the same explanation. So again, we're filling in those electrons. We could say something closer to octet rule as well. So just filling our shell. Questions about those at all? Or again, anything else? So just going back right to the electrons, I don't know if it helps to kind of visually. Yeah, so we could write it out if this helps more. So if we do like phosphorus versus chlorine here, and we're in the 3p, so phosphorus has 5 valence electrons, right? And we're looking at our 3p versus chlorine, which has 7. And so it's just that effective nuclear charge, right, of adding more electrons at that same radius, so in the same energy level, filling it up. And so that just gives it greater effective nuclear charge and kind of tightens it. So like kind of going back to forces, so the greater your charge is over your radius, right, then the more attracted things are. All right, let's practice. Yeah, or you could like draw this same diagram because it's the same effect, right? That it's like, okay, greater effective charge, so that's also going to make it more difficult to kick one off if they're being held tightly together. So let's try a temperature conversion one. And you might have like a different one on the exam potentially, like a different temperature conversion, I mean, so just read. So let's do convert 333 degrees Fahrenheit to degrees Celsius given, and this should just be our normal formula, that TF minus 32 times 5/9 is equal to our temperature Celsius. So see if you can plug that in. Did we get a chance to plug it in? What do we get? So 167, thumbs up on that. So excellent. I see a lot of yeses, and I'll just plug it in. So please excuse my dear Aunt Sally. Right, order of operations. So obviously parentheses first times 5/9, but it sounds like you guys got that. And then we'll probably just round to 167, right, for our 3 sig figs there. So yeah, just watch sig figs on these. That's the only like real comment I have after grading. I think I finally caught up on grading. By the way, I may have missed a few things entering, but I'm gonna hand back a bunch of papers. But that's the only thing is right. However many sig figs you start with, make sure you end with the same sig figs. So that can be a little confusing when doing the converting. So just kind of watch that. That was like the only minor criticism I had, but I mean, really good work from everybody, so. All right, let's try this. This one is kind of a trickier one that you might see. So a sheet, particle board is cut to a length of 6 feet and a width of 3.50 feet. It weighs 60 pounds. So given that your density is 53.7 pounds per foot cubed, what is the thickness of the board? So I'll give people, I want you guys to stew on this for a little bit, right? Think about what we know, some of our formulas. Maybe I'll give people a formula hint in a little bit, but just try to think about it. Did we at least come up with some formulas for this one? What are we kind of thinking so far? Any formulas that people are kind of thinking of? You don't have to have an answer yet, but just trying to push people in the right direction if you're stalled out. Oh, yeah. So volume would be a good one. So what's kind of our typical volume formula? Oh, yeah, so you were thinking, so density equals mass over volume, and then, yeah, rearranging, so volume, mass over density, good. Is there another volume formula that that we also know? I kind of try to hint at it with this. Yep, so length with height. So yeah, that's pretty much all you need is those formulas. So I'll give you guys another minute or so to finish calculating and stewing. I'll try to hand back more papers. All right, so let's kind of continue where we left off because I think you'd mentioned that we need to find the volume anyways, right, of our, well, rearranging our formula. So we have mass, we have density, so we could start with that. So just writing it out. So again, volume equals our mass over our density. So plugging in 60 pounds divided by density. So feet cubed goes on top. 53.7 pounds on bottom. So cancel out. To give you 60 divided by 53.7. And then we get about, so 1.117 or so. Try not to round too much. before the n feet cubed. So ideally you just want to leave it in your calculator until the end on these. And then, okay, like you guys also mentioned, well, we have this other formula for volume, right? Length times width times height. And they did give us, right, 2 dimensions. And so now we can solve for our height of our board, or thickness. And so now let's plug that in. So our volume is equal to, and then just watch your units, right? So they did give it to us in feet. So that's all fine. So 6 feet times 3.50 feet times our height. And so now we can solve. And so we should get 0.053 feet there. Or, well, 3 sig figs, so we should round it 0.0532. And that's, again, in feet there. Yeah, yeah, that's fine. Yeah, I'm totally cool with, web calculators. Again, there's there's a difference between like Mathematica, or I don't know what you're using, Desmos. Sorry? Oh yeah, Wolfram Alpha is, I'm glad it's still going strong. That's my favorite. But yeah, Wolfram Alpha is nice, or Desmos, those are like the ones I'm familiar with, but any online calculator is fine as well. All right, this might be a good spot just for a little break, and then we'll shift to electron configurations and kind of other new stuff. And so again, just ask questions, right? Or if anything has come up. I think I just need to enter in some people's quizzes, and then that should be everything, hopefully, that people have turned into me. Should have made their way back to you. I just got an email about a quiz correction, so I may be a little behind on the My Open Math, but now's a good time to nudge me so that I can finish reconciling, since I have to do it manually. But yeah, just give me a little nudge, make sure your grades are up to date. That sounds good. So yeah, we'll take a break. All right, let's look at another type of question. So I'll write it out as people kind of still make their way back. And so now this is about average atomic mass, right? And so it kind of going back, our average atomic mass on our periodic table is equal to the sum of, right, our percent of our abundance of isotope 1 times, right, mass of isotope 1, and then, right, etc. for n, so you keep adding it, kind of like we did in lab. And so now here's kind of a special scenario. And so we'll look at this. So gallium has 2 isotopes. And so that's kind of the key in this type of question that we'll see on the exam. And the average atomic mass is 69.723 AMU. And so let's just say that gallium 69 then has a mass of 68.9253 AMU. And then gallium 71 has an atomic mass of 70.9247 AMU. And so given that information, what's the percent abundance of each? So again, I'll let you guys kind of try it, stew on it for a little bit, right? How would you set it up? And then we'll go over it together. So did we come up with a way on how to approach this problem, or? Yeah, so kind of walk me through that process. So nice. So yeah, I would do something kind of similar. Uh, so what he's saying, right? So everybody can kind of follow along. So you set 1 to x, right? But kind of the whole thing with those two isotopes is that you just have two variables, right? So you could write it out as x plus y equals. I mean, he did this like 1 over 100 thing. What I ended up doing is, okay, you have it this in percentages. I went to decimals, but like I said, his formula sounded fine since he was getting percentages. I'll show you how I worked it out, like I said, in decimals, right? So x plus y equals 1, and then you get this y equals 1 minus x. So that's really the trick there. So then you have your two variables. Yeah, I mean, I was just kind of being like super explicit, but yeah, you could have definitely jumped that it's just 1 minus x, since again, that's kind of your only option with 2. And then just set up the algebra, again, just like he went through. Like I said, mine will be slightly different since I'll get the decimal percentage. So I'll sketch out my work, right? So our average is equal to x times 68.9253 plus 1 minus x. And again, that's really the hardest part, which isn't too bad, is just distributing, right, this now. And so at this point, it's just algebra once you get to here. So again, I mean, this is kind of more for the in-person people. Although with the online, you still have like this option to upload. So you can like type in your work, but otherwise you can also upload uh, pictures and stuff. So a lot of people do that for the online exam, especially if you don't have time to like type it all out, right? So again, you just want to show your work. So in case you do mess up the algebra, I can give you appropriate partial credit, especially like I said on the free responses. But at this point, all right, just algebra, distribute, so I'll write it all out. And then group our variables. And move it to the other side. Sorry, I'm trying to pull it up. Because it depends which format you take. So online, I want to say there's like 50 questions or something. And in person, I think it's shorter, but there might be more free response. Sorry, let me pull up your current exam. Well, I'll look at the number of questions in a second. Let me finish algebraing all this. So I have, sorry. So negative 1.9994x on one side. And then, right, I need to take my 69, probably move the 70 over, subtract that. So now 69.723 minus 70.9247. So negative 1.2017. So then we get something like that. And then solve for x. So just divide. And so you get about 60%, right, for x, or again, assuming that you set x to our 69 gallium. So then we can rewrite it. So 69 gallium, sorry, is equal to about 60% then. And again, just make sure you convert appropriately. And then that makes our 71 gallium about 40%. We should be consistent. I wasn't very consistent. So we were given 5, so technically we should round it to like 5 sig figs. I just kind of, as long as you're in the ballpark for these ones. So sorry, let me try to get an answer. On the midterms. So yeah, the online version has 51 questions. I think it's slightly shorter time limit of like 100 minutes. And the exams tend to be time intensive. I think the in-person may allow a little more time, but like I said, it's kind of hard to compare. So if anybody wants to take both, but I certainly don't expect that. And then let me look at the in-person one real quick. Sorry. Yeah, I mean, that would be fair. I'd be curious, but yeah, I mean, it's totally up to you. Like I said, I don't want to like stress people out. But if anyone online wanted to take like the paper version and email it that back and forth, that would also be fine. Let's see. So we look. So the problem with the in-person exam, so it's 13 questions, but then, so like part 1 has like 1, 2, 3, 5 parts, but it should be pretty quick. So yeah, I think it's more like free response, see the in-person exam, but it's like shorter. So I don't know. You guys can tell me. I like the in-person exam better, but that's just me. But anyways, we can debate philosophies of teaching and exam styles later. But yeah, that kind of gives you an idea. All right, let's go back to our review. So let's see, so you'll have some easy ones, or at least hopefully easy, like electron configuration. So let's practice a few. So let's try antimony. Let's try sulfur 2 minus, so notice the charge on it. Let's try tin 2 plus. And tantalum. So I'll give you all a few minutes to try that one. try those. All right, let's start to go over these. Looks like people are finishing up. So we can probably just kind of start yelling it out, and we probably want to do noble gas configuration. So what should we start with for antimony here? So krypton, so you said 5s2. So that looks good to me. And so I'll just put a P table so everyone can see. So again, just kind of going through that. So antimony, so go back to your previous noble gas. And then excellent row 5, so 5s2. Make sure you have that label just like you said, 4d10. And then back to 5p3 there. So that looks good. Everybody like that? No questions? Alright, so that one was simple enough, hopefully. What about sulfur? And then notice, right, it was 2 minus. And then what noble gas should we start with? So neon. Excellent. So neon 3s2, 3p6. Let's just pull up p table so we're all looking at it. So good. So sulfur going back to neon. Again, that row 3. Good. And then, of course, -2, so bringing us right to 3p6 there for those 2 extra electrons. Questions on that? And then let's try, so 10, 2 plus. So again, what noble gas should we start off with? Krypton 5s2. Would you say 40? Yeah, I would double check maybe. Oh, oh, but it's, yeah, it's 2 plus, so yeah, we're okay to stop. Yeah, so normally, right, if it was a neutral, we would have the P. And then what's kind of cool, sorry, let me rewrite my 4D, that looks terrible. What's kind of cool about this is we can start to see why tin has 2 different oxidation states, right? So if you remember, it could be tin 2 plus or tin 4 plus. So the tin 2 plus, right, is pulling, and I'll write this off to the side, right? But our neutral would then have had those p electrons, right? So those we can tell were knocked off first, so that gives us our 2 plus oxidation state. And then if we keep going, it would likely pull from the s, right, to give us the 4 plus oxidation state, and probably leave all those d electrons alone, right, since they're all happy, filled, satisfied. So kind of cool there. All right, good job with that one. And then the last one, tantalum. And then where do we start? So it was over here. So xenon 6s2. And then what'd you say? And then what about, we're missing something. Yep, 4f14. Excellent. So remember, you start the F on the 4, so good job for remembering that. Y goes back to like the quantum mechanics that it's not until the 4th energy level where you have F orbitals, but that's our first one, yeah. Oh, because the F only holds 14. So that goes back to what we've said. It's like even though you look at that one and it's 15 across, the F is only 14 and the other one comes from the D's, right? So then that's why it's 5D3 there. And so don't forget, if you're, a little confused on any of these, double check your total count, right? So we said we started with xenon, so that'd be 54. So let me get out my calculator. So 54, and then plus 2, plus 14, plus 3 there. So then that gives us 73. And then that matches, right, for tantalum of 73 there. So that's why it's 4F14, and then this, remember, is the D's, right? So this is 5D1, 2, 3. Yeah. That's the best way to consider it when we're doing the electron counting, right? Because like we said, if we were to actually research it, there's arguments that lutetium and lawrencium are more D block in character, but again, that's like for the chemists that care about that to argue about. That's not even like my area of chemistry. Yeah, again, for our electron counting purposes, right? So I would do 7s2 and then start this as, so 3, 4, 5, 60, right? So then 61, and then start the F block here. But like I said, there could be minor discrepancies. That's okay because of the confusion that we've discussed. And then again, you can always kind of check P table. So we click on actinum here. Oops. Sorry, trying to click on this and scroll up. So it does match with what we said, right? Where if you can read that, like I said, I can't zoom in, but it does say 61 there. So that, again, kind of fill as we expect. But again, we won't get into the characters of that. All right, let's try another type of question. Let's see if I can get a fatter pen. All right, let's say we have a new element, has an atomic number of 135, a mass number of 288. Find the protons, neutrons, and electrons of an ion with a 4 plus charge. Oh, wait, give people a second. So yeah, we'll give everybody a minute or so to think about it. Oh, some of y'all are fast on that, which is good. All right, now you can tell me what you were going to say. Sorry, 135 protons, and then I didn't hear you. 1. Perfect. I like it. Did we have questions on that? Do we remember how to get everything? So remember, mass is just protons plus neutrons. For the charge, I like to think of it as protons plus electrons, but again, electrons are negative, so it's like you're adding a negative. And then everything falls into place. You can ask questions, or else we'll just keep moving on. All right, so this is kind of definitely more for the in-person folks with how I worded things on the in-person exam. Like I said, if anyone wants to give me feedback on them both, I'm always curious. And so how it's going to be worded is it says give the chemical formula and name of the following compounds from the pairs. So then you'll have kind of two pairs. And so again, give people time to work through this. So what would the compound be named if we have chromium 3 and phosphorus together? So again, what would their balance formula be? What would be the proper name? And then the other pair, so you'll have 4 pairs. So ammonium and sulfur. So again, what does that pairing look like? How do you properly name it? Silver and phosphate. And then tungsten 3 and oxygen. And then one more phosphorus and sulfur. And then given that there are 2 atoms, phosphorus in this compound and 3 of sulfur. So again, how do you give the proper name and the proper formula for those 5 combinations? So I'll give people, like I said, a few minutes to kind of work on them, and then we'll go over them all together. All right, let's see what we're thinking. So what do we get for this chromium 3 and phosphorus? So give me either the formula. So chromium, just don't forget the 3, right? So chromium 3 phosphide. Oops, phos. Yeah. Yeah, just because chromium's a transition metal, even though it is in the 3 plus oxidation state a lot, I mean, it can still be 6, so we want to specify. All right, what about ammonium and sulfur? What's our proper formula? Yeah, we just and then we don't need to specify it, but good. So write -2 on the sulfur, ammonium, just kind of sketching out the work was +1, so then good. We had two of them. Excellent. So ammonium sulfide. Good. And then so usually I'm not too picky about spellings, but right, I am looking for the "ide" on those endings, but like I said, I'll probably be forgiving of other misspellings. So online auto grading is always an issue. Obviously in person I can be generous, but again, just if anything happens online, just email me. All right, what about silver and phosphate? What's our formula? And then how many AGs do we need though? Yeah, 3, right? So phosphate, PO4, 3 minus. Silver, like we've said, for our purposes is always, always, always 1 plus. Uh, and so, and then how do we name it then? Silver phosphate. Good. All right, what about this next one? So, a tungsten in a 3 plus oxidation state and oxygen. So W2O3 looks good, right? So tungsten 3 plus, oxygen's typically -2. And then kind of the easiest is to do that swap trick and then double check yourself. So 3 times 2 is +6, -2 times 3, -6. So they balance. And then what's our proper naming? Excellent. So tungsten 3 oxide. All right, good. And then our last one. So the formula should be pretty easy, at least. So P2S3, and again, right, so that's our hint. It's a covalent compound. It can be in any ratio, so then we need our prefixes to tell us. So what's our name? I like it. And again, I'll be forgiving on all these crazy vowels and stuff that can happen. Just keep the "ide" ending and all that. All right, that looks good there. All right, the last type of question that we'll have, and like I said, this is in person, so there'll be like multiple choice, free response and stuff, or kind of geometry for online exam, just slightly different format. And then probably, oh, sorry. No, the in person is more free response, but less questions. So it's like, I don't know. I don't want to go off on like how people perform right now. Because I feel like people like, anyways, I've already said too much. So let's try, we can discuss exam philosophies later after class. Let's just try our practice problem. So see if you can draw our Lewis dot structure. For NO3, and then see if you can answer if it's polar or non-polar. So just kind of draw it out, and there could be, remember how we went over that there are resonance structures sometimes? So there could be resonance structures. So yeah, just try to draw it like one way. So let's kind of sketch out a few things. So the most important thing that I really care about is our electron count, because again, you've kind of hinted at it. It's like, well, how do we know if it's single bond, double bond? Well, we can play with that, right? Remember, we can play with our resonance structures, but all right, so then let's figure out how many total electrons we have to have in our system. So how many do we get from nitrogen? And then each oxygen. And then our negative charge, right? So then 24 electrons total to play with in our system. And so you could have started off, but then the negative charge, right? Because our polyatomics have a certain charge, so then this one has an extra electron, so 24. And you could have started off with kind of the most basic structure of just a single line to everybody, and then filling in the electrons, right? So 8 times 3 is 24. But then, for more complete understanding, we want to put our formal charges. So remember, formal charge is number of valence electrons minus individual atoms. So this is again from the periodic table. And then this is individual, I can't spell. Let me try that again. Right, so counting your individual electrons on your atom. So 6 minus 1, 2, 3, 4, 5, 6 minus number of bonds. So minus 1. So that gives us -1 for all of these. And then formal charge on nitrogen. Again, same thing. So this is oxygen, nitrogen, so same thing. 5 minus 1, 2, 3 gives us 2 plus. And so then what other structures did we maybe draw then. Is it though? Yeah, so how many things does it have attached to it? So 3, so then that makes it flat, so trigonal, planar. But then, okay, so that's good. But then what other resonance structures can we draw? What can we do with these electrons? Maybe make some double bonds. So what do we have? And there's some criticisms of this structure, right? That like this is not the best one. So not only do we have these formal charges, but what's our total electron count on nitrogen? So double, yeah, so count the lines, so it should be not 5, but you're close. So 6, right? Because each line is 2. So 1, 2, 3, 4, 5, 6. So yeah, nitrogen is only feeling 6 total electrons. So okay, maybe this isn't our best structure. So did other people draw something else? Did we put any double bonds in there? So let's look at that. So again, you can kind of make arguments for all these resonance structures. And so let's just make 2 double bonds, right? Because that will get rid of the formal charges. But then let's see what that does to something else. Oops, I don't know. There we go. So we still have, right, 8, 8, 8. So still 24 total electrons. This oxygen still has a negative formal charge, which is good, right? It has to match the charge of nitrate. But what's funny about this one? What's a little criticism? Yeah. Yeah, so I was just filling up to 28, right? Yeah, so then oxygen satisfied by octet rule 1, 2, 3, 4, 5, 6, 7, 8 on this one. So that's good. It's just the nitrogen is my criticism, right, for this structure. And then what's kind of the issue with nitrogen in this structure? Yeah, so now, right, we see this, that it's a second row, and so it has 10 electrons, and so nitrogen just typically isn't hypervalent. I'm not saying that this isn't necessarily valid or invalid. Sorry, I totally misspelled that. Hypervalent. But again, this is where we get into, right, computational chemistry would actually give us a better true sense of the electron density. But just looking at that, hypervalent. So then probably the best resonance structure is just 1 double bond. And again, it would kind of be averaged and rotated around. And again, modeling would give us a better sense of the true nature. But this is my best kind of resonance structure. And again, for our level, right, I would be happy if you drew this structure, or even this one's okay, right? Just maybe point out that it has 10 electrons. So that's again like the point is like, can you look at your structure? Can you point out maybe what's odd about it? So again, being able to recognize, well, I can draw this. It has the correct number of electrons, but writing these formal charges, that's good, and recognizing that nitrogen is electron deficient, and again, just identifying it, right? So you identify it, that tells me at least you're thinking. And then if you see this, right, maybe try to draw a better one that doesn't violate the rules so much. And so again, this one is kind of our best one with 24 electrons total. Right, nitrogen has the octet rule, same as our oxygens are all satisfied by the octet rule. You know, we do have a few formal charges, but once we try to get rid of them, right, then we start violating the octet rule. So we're always trying to balance kind of all these rules out. And like I said, we're really trying to do quantum mechanics with just like little dots and arrows. So it's even kind of amazing we can make these many conclusions. So, all right, we're kind of at our time, but that does cover, like I said, the in-person exam pretty thoroughly. The online one is going to have the same concepts, just again in different formats for different places. So, yes, exactly, nonpolar. Thank you for reminding me. So nonpolar, since again it'll even out our vector forces. And then I am around if there are any other questions or things that have come up. Like I said, I should have handed back everything. Email me if there are minor grade corrections as you've already done, so I will get on that. And otherwise, I'll see you all definitely Wednesday for lab. And then otherwise, good luck on the exam, no matter which format you take it. Yeah, I would appreciate an email if you're in person, just so I kind of know where you're at. But at least just take the exam somewhere. All right, have a good one. I'll stay on stream for a minute or so if there are questions, but yeah, I'll be around too. Yeah, you can hang on to the homework to study. Yeah, that's fine. Yeah, I don't mind. Yeah. And I could still be behind on the My Open Math stuff. So I think I need to take another pass and fill in some quiz grades for people, but you can also gently remind me and I will fix that. I'm finally catching up to my grading, I believe.